Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, and thank you for joining us on the podcast we call Space Nuts. It's great to have you along for yet another episode, and joining me as always is astronomer Fred Watson. Hello, Fred.
Hello, Andrew. How are you doing?
I'm good. I'm very well. And hello to Mandu. I know he's lurking nearby. I heard him earlier.
Yeah, he's just gone back to sleep.
Oh, has he?
Yeah, I think he... Yeah.
And for those who are new to the podcast and don't know what we're talking about Fred's cat, Mandu. Get it? Yeah. Now, today we are talking about the first direct evidence that's showing there is water ice on the moon. It's like black holes. We know they exist, but we've never seen one, and that's been the case for water ice on the moon, apparently. So now we think we've spotted some. There's also a new home for Iron Man, it appears. That is the planet Kelt 9b, which has a very unusual atmosphere. And we're going to try and tackle three questions from 2 listeners today. One about the expansion of the universe and a follow-up to our discussion about black holes, which I think was a follow-up to a discussion about black holes, if I remember rightly. But we'll get to those a little later. But Fred, the first direct evidence of water ice on the moon, I suppose we should start by talking about the fact that other forms of ice exist in the universe, and we've certainly found evidence of that.
That's right. Yes, ice. We tend to use the word ice for anything that's liquid at the kind of temperatures that we deal with, and is not liquid at the temperatures that we often find. And I guess the commonest is dry ice, which of course is solid carbon dioxide, and that's found around the poles of Mars. But what we're talking about now is definitely water ice, good old H2O, but at a temperature below zero. This story goes back actually to the early 1960s, believe it or not, when people speculated that, because by then we knew that some of the craters on the moon near its north and south poles, because they never ever see sunlight, and so in the bottom of the craters, and so the speculation was that we might find all kinds of interesting things there, and one of them was that water ice might exist in these permanently shaded areas. Moving on a few decades, there have been detections of a kind of smoking gun for ice, if I can mix all the metaphors,
sure.
By spacecraft like NASA's Lunar Reconnaissance Orbiter and the Indian orbiter Chandrayaan-1, which did an amazing job at detecting hydrogen above the north and south poles of the moon. So both of those spacecraft have picked up hydrogen in the sort of I was going to call it a rarefied atmosphere, but even that's gracing it with too strong a term. It's just a few atoms that basically leak up from the surface of the moon. But hydrogen is amongst them. And hydrogen is what you expect if you have a body of either water or frozen water, in other words, ice.
Yep.
So the interpretation has always been that was as I said, a smoking gun for ice. But there are other possibilities there. And there is a scientist, Dr. Shuai Lee, who's at the University of Hawaii. He has made the comment that, yes, it could be just hydrogen that's coming up from the moon. It could be hydroxyl, which is another molecule that has oxygen and hydrogen in it, or it could be water, or it could be anything else with hydrogen. What he says is the early data could not distinguish which is which. And so what he has done, he and his team of colleagues in the University of Hawaii and elsewhere, they've used an analysis of data from an instrument called the Moon Mineralogy Mapper, which was also on the Chandrayaan-1 spacecraft, and it essentially looks at the spectra. It measures the rainbow spectrum of the surface that it's flying over. Mm-hmm. But it does that in the infrared. That's the redder than red region of the spectrum, invisible to our eyes. And so they've done a very careful analysis of the data that you get when you fly over the north and south poles of the moon. And sure enough, they have identified the signature, the fingerprint, if I can once again mix metaphors, the fingerprint of water ice. So this is definitely water ice. It's got a characteristic spectral signature which they've detected in many, many spots above both the north and the south pole of the moon. It turns out actually that there's more of it down in the south. There are larger areas of water ice in the southern polar region, and that's probably because the craters are deeper there. So you've got.
I thought it was because that was the bottom of the moon, and that's just naturally where water would drain.
Yes,
someone would believe that if you really tried to convince them.
Yeah. No, look, it's only the bottom of the moon seen from our, northern centric view of the universe. If you're standing there, it's the top of the moon, I can tell you. So yes, it's like it's just spots of water ice, but there are more of them in the south than in the north.
Now, this is a pretty important discovery because water ice means potential for, maybe habitation, but it also means that making fuel becomes a real thing.
Exactly, that's right.
And they are talking about going back to the moon, and there was an article this week that argued that we should be focusing more on the moon now than Mars, and raising all sorts of reasons why, which I won't go into. But there's definitely plans to go back to the moon. China's definitely keen to get there.
Yeah, actually, indeed, and other countries as well. The Indians have got their sights on the moon as well, and they've done such a fantastic job with Chandrayaan-1. It's been a very successful project. I think it's now defunct. I can't actually remember. I think that spacecraft no longer exists. But yeah, what you've said is absolutely right. If you can find stores of water on an alien world, then it absolves you from having to really worry too much about finding fuel, because if you can put solar panels there and dissociate the water into hydrogen and oxygen, what you've got is rocket fuel.
Yeah, which is very handy stuff when you want to get off something and get back to Earth.
Yeah.
The other interesting thing is it's pretty inhospitable terrain, that part of the moon. It's I believe, if not the coldest place in the solar system, very close to being the coldest place in the solar system.
It's very, very cold, that's right. The figure I've got is minus 238 degrees Celsius.
And for you Americans, that's minus several million degrees.
Fahrenheit. It's very cold. I think, actually, I have a feeling Pluto is minus 239. I can't remember. Yeah. It's very cold out there in the dim and distant bits of the solar system.
So what happens now that they've confirmed beyond reasonable doubt that there's water ice on the moon? Everyone just goes, "You ripper," clanks their glasses together and gets on with it.
Yeah, look, it's just additional knowledge. I mean, one of the interesting things that we see from this, though, is that this is it's rather different from ice deposits that we know are elsewhere at the northern and southern poles, and they are on the planet Mercury, and that's even more weird because Mercury is so close to the sun, but it does have ice deposits near its northern and southern poles, and Ceres, the dwarf planet Ceres, which is out there in the asteroid belt. A very interesting world for all kinds of reasons. It's still, I think, being orbited by the Dawn spacecraft, a NASA spacecraft. But they have kind of much larger areas of ice rather than just these spots of ice that have been found on the moon. And that, that raises questions itself. So there will be more research done on this to find out why the ice is patchy rather than, these contiguous areas.
Probably just mixed up with the soil or something like that.
That's a possibility, yeah.
It also opens the door to the probability that water ice is more abundant in the universe than we probably have ever considered.
I think that's a lesson that we've already learned, Andrew, because, we see it everywhere. Compared with even only 10 years ago, if somebody had said, well, these are moons of Jupiter and Saturn, a lot of it is ice, and then there's a lot of water there as well. In fact, there's more water on Titan and I think Europa, it might be, one of the moons of Jupiter, more liquid water than there is in all the oceans of the Earth. So we're realizing just how abundant it is. It's not really a surprise because the radio astronomers have been telling us for years, for decades, that the most common two-element molecule in the universe is water. So, because you can pick it up as a vapor by telescopes, just in interstellar space, in nebulae and things like that. Water is everywhere.
Yes, and it sort of brings back into play that four-letter word we occasionally bring up, which is life. The L word. Where there is liquid water, there may well be life. So
there may well be, but that's a lesson that we have yet to confirm.
Yes, indeed. But the good news is we have confirmed beyond doubt that there is water ice on the moon, so close to us. So that's a big leap forward in our knowledge, and very handy to know.
Yeah.
And the launch of TAP-1, the next big mission to the moon, is not far away. You're listening to Space Nuts with Andrew Dunkley and Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, from the moon that we know and love to a place that we don't know and probably wouldn't love if we had to move there, it's Kelt 9b, one of the strangest planets that has yet been discovered. It's an exoplanet, of course. What's fascinating about this is they've just announced that it's got a very strange metallic atmosphere.
That's correct. A very strange world, and the strangeness comes because its temperature, its surface temperature, is more what we would associate with a star than a planet. 3,780 Celsius.
Gee.
Whatever that is in Fahrenheit. It's very, very hot.
I could find out for you if you like.
Yeah, I could too. But
hang on, give me a sec. Hey Siri, what's 3,780 degrees Celsius in Fahrenheit? And the answer is 6,836.
Show off. Just because you've got Siri on your wrist.
Very handy.
I switch Siri off every time she shows up.
I find it very handy on radio when I need to make a quick calculation about something, because a lot of stories turn up in miles an hour or feet and yards, and I have to convert it for an Australian audience. So very, very handy indeed. So anyway, it's a hot place.
All right. From one total digression to another, you and I are used to talking about exoplanets with names like Kepler 128 and Kepler 936 and things like that. But this is Kelt, and I bet you don't know what Kelt stands for.
Well, no.
Yeah. Where's your Siri now?
If I asked, I'd probably get some explanation or definition of seaweed.
Something you'd rather not have. That's right. Yes, you probably would. It's an acronym for the Kilodegree Extremely Little Telescope. That's what it stands for. And the kilodegree means it looks at thousands of degrees. That's to say it's got a very wide angle of view, and that you would associate with an extremely little telescope, because the smaller it is, often the bigger the angle of view. But it's doing the same sort of job as Kepler. It's looking for eclipses of stars by their planets. In other words, or not so much eclipses where things disappear altogether, but when a planet transits in front of its parent star and the light of the star drops. So Kelt has found a very large number of these things, and it's got a lovely name. I like the extremely little telescope
I
bit.
do too. That's cute.
Yeah. So Kelt 9b. Okay. So the data that we're talking about now don't come from Kelt itself. They come from actually an instrument on a very large telescope in the Canary Islands, the TNG, Telescopio Nazionale Galileo, and that has an instrument called HARPS North. HARPS is I forgot what the acronym stands for, but it's once again it's a method of measuring the spectra, the rainbow colours in the light of a star. And if a planet with an atmosphere passes in front of the star, you can actually see what the atmosphere does to the light in terms of its spectrum. And HARPS is an instrument that analyses that very successfully.
HARPS stands for, has anyone really programmed Siri?
Right. Thanks, Siri, and thanks, Andrew.
No worries.
Right.
Always useful.
Yeah. I'm embarrassed I can't remember what it stands for. It's a vacuum spectrograph, and it's for planetary searches, but it doesn't matter. That's fine. I think the HA might be high accuracy. There you go.
Where were we? So this planet is super hot with a strange atmosphere.
And it's been observed in La Palma in the Canary Islands, where I used to work. There you are. There's another throw-in for you. So okay, what have we discovered? First of all, this thing is not nearby, relatively speaking. It's quite a long way away, 620 light years from the Earth. It's in the northern hemisphere constellation of Cygnus, and it's classified as what you call a hot Jupiter, which is a gas giant, but very close to its parent star. This one is much bigger than Jupiter, 3 times the size, and so close to its parent star, it's got this 3,780 degrees Celsius temperature, hottest exoplanet ever found.
Wow. It sounds like it's so close to being a star. Could it be like a failed binary star system, perhaps?
Yes, it almost makes you wonder. I mean, if it's 3 times the size of Jupiter, that means its mass must be considerably more if it's diameter we're talking about. And once you get to above 13 Jupiter masses, Andrew, as I'm sure you'll remember, what you've got is a brown dwarf, not a black hole. A brown dwarf star is defined as being an object with more than 13 times the mass of Jupiter. So I suspect this is below that level, but it's still stellar-like in its temperature, and because of the hot, the heat of that temperature, it means that the elements or the substances that have been detected in the atmosphere are not molecules. Molecules which are atoms paired together, like the water molecule we were just talking about a few minutes ago. Molecules don't like high temperatures. They break up into their component atoms. And so what we find here is elements rather than molecules. And the elements that have been attracting the headlines are, first of all, iron, as you mentioned. It's got iron in its atmosphere, and titanium, another kind of more exotic metal, which we actually find quite commonly in the atmospheres of cool stars, but it's bound up then with oxygen. It becomes an oxide of titanium in these atmospheres. So I think this is one of the first times that titanium, atomic titanium has been detected certainly in the atmosphere of an exoplanet, but actually at all in space. I think it's a bit of a rarity. So very interesting stuff, and it's pretty hard to imagine what it might be like standing on the surface of a planet with if it has
titanium,
with an iron and titanium atmosphere. That's right.
Well, Paul McCartney wrote a very famous song about Magneto and Titanium Man, and maybe if Iron Man and those other two got together, it'd be perfect for them. They'd live happily ever after.
One would hope so. They certainly would never be cold.
No, definitely not. As discovered by, you ready for this? The High Accuracy Radial Velocity Planet Searcher.
There you go.
That's
so
what
I was
HARP
right.
stands for.
I was right with the high accuracy.
You were. You got.
And I should have
right.
radial velocity planet.
Yes,
so.
but that planet Kelt 9b, one of the weirdest ever discovered. But I am sure, Fred, there are weirder places out there yet to be found.
I think that's right. I think
one of them could be Earth.
Well, to some outside observers, if there are any, the Earth will be very strange, because I think we've kind of concluded to some extent that higher order life forms of the kind that we find on Earth might be very rare in the universe.
Indeed. All right, we'll watch with interest. You're listening to Space Nuts. Andrew Dunkley and Fred Watson here.
0G, and I feel fine.
Space Nuts.
Finally, Fred, as we like to do, we'll finish off with a question. In fact, we've got, I think, 3 questions from 2 sources. We'll start with Dan Hind. Hello, Dan. Thanks for your question. Hi, Fred and Andrew. I'm a long-time lurker. First time question. Is the universe expanding at a uniform speed? And if so, how do we know? Also, following on from the black hole question this week, if black holes are considered a point of infinite density, why do they vary in size? Shouldn't they all be the same? I suspect I've got more than 3 questions for you today, Fred. Might be about 7. But yes, is the universe expanding at a uniform speed was the first part of Dan's question.
Let's deal with that, yeah. And the answer is no. Since the 1970s, we've had the wherewithal to kind of chart the expansion speed of the universe to some extent through its history. We used to think that the universe's expansion was probably slowing down. And that would be because the expansion itself comes from the Big Bang, but the universe is full of matter, which has gravity and tends to slow it down to break the acceleration or break the expansion. But since 1998, we've known that that's not the case, that the universe is now expanding more rapidly than it used to. And in fact, the acceleration seems to have kicked in about 6 or 7 billion years ago. So remember, the universe is 13.8 billion years old. So about halfway through the universe's current lifetime, it seems to have started accelerating more rapidly. That doesn't really tell us whether that expansion is something new that's kicked in, or something that's always been there, and we think it's called dark energy, that's always been there. But in the early universe, the gravity of the things in the universe actually was strong enough to stop the acceleration showing up. I don't know whether you're following all that. It's a fairly esoteric argument, but so we think that since about 6 or 7 billion years ago, the universe has started to accelerate in its expansion. How do we know this? Because we have standard candles, and the standard candles are things called Type 1a supernovae. They're exploding stars that always seem to reach the same level of brightness when they go off.
Okay.
And that makes them very useful because they act as what we in the trade call a standard candle. In other words, a standard light intensity. And so what we can do is measure where these things sort of should be if the universe is expanding uniformly, but then see where they are because we know how bright they intrinsically are. And it's that comparison, along with some rather more esoteric considerations, but that comparison leads you to the deduction that, yes, the universe is expanding more rapidly. Okay, that's the first two.
Yes. Also a follow-up on the black hole question.
Yeah, so
if black holes are considered a point of infinite density, like my brain, why do they vary in size? Shouldn't they all be the same?
Yeah, and it's a great question, and it just tells you that black holes really don't behave in the way we intuitively expect. Because even though, yes, a black hole is a point of infinite density, they do vary in mass. And by mass here we mean their sort of gravitational influence. I guess you'd call it their gravitational mass rather than their inertial mass. There's subtleties here that we don't really need to go into, but the bottom line is that the more stuff you pile into this singularity, even though its density is infinite, the more massive its effect is on the space surrounding it. That's probably the best way to look at it. It's what is its effect on its surroundings. And the more massive, the more stuff you pile in, the more massive it becomes, which is why we sometimes get these billion solar mass black holes at the centers of galaxies. Quite extraordinary stuff.
And up until recently, we couldn't figure out why they were only coming in two sizes, small and massive, and then I think 2 weeks after you and I discussed that, they found a medium-sized one.
They did, yeah. The medium-sized ones are still pretty rare, though. Or to give it the technical term, Andrew, an intermediate mass black hole.
Right. Sounds better than middle-sized.
Yeah.
Okay, so hopefully that covers your questions, Dan. We'll move on to John's question because it actually dovetails with Dan's.
It does, very nice.
John Milton, and thank you for your question, John. Questions. I've been listening to your August 16 podcast. Oh, that makes three of us, where you discussed singularities. I have two questions. One, since time slows as you approach a singularity, has any matter that's fallen beyond the event horizon actually reached the singularity yet? Do you want me to read the rest, or do you want to tackle that first?
No, let's do that one first, because that's, I think, relatively straightforward. So time slows down, but that is as you are viewed from an outside observer. So what it means is that an outside observer would see you or not because you're inside the event horizon. But to an outside observer, your time is slowing down. And so an outside observer sees your fall gradually slowing. In fact, I think time stops for you on the event horizon. So to an outside observer, I can't say the word, an outside observer, you see all these poor people splattered on the outside of the event horizon, but the person themselves have actually passed through the event horizon without noticing any change in time. They just whiz towards the black hole because they themselves perceive time at their normal rate, but actually it's slowed down for them. Does that make sense? I know it's difficult stuff.
It doesn't make any sense whatsoever, but your explanation did. I think they portray this concept really, really well in the science fiction movie Interstellar. Yeah, where they go down onto the surface of a planet which is very close to a black hole, but the spaceship they travel to the area on is further away, and so when they travel down to the down to the planet's surface, time for them is as it feels, regardless of where they are. Yep. But for every hour they're down there, 7 years passes on the spaceship.
That's correct. Yes, that's right.
It sort of gives you a rudimentary understanding of the effect of a black hole.
Yeah. Whereas if you were on the spaceship, you'd see time, going normally as well. Even though it's the difference between them, exactly as you've said. It's the difference between these two reference frames, as we call it in the trade.
So, That's part one of John's question. Second part is, if matter beyond the event horizon retains angular momentum, presumably it orbits the singularity faster as the distance decreases, but wouldn't this fall be halted when its orbit velocity reached light speed? Yeah.
Well, no, that's another great question. These are really perceptive questions about the way black holes work, and black holes are a puzzle for all of us. But the answer is okay. So nothing can travel faster than the speed of light, even inside a black hole event horizon. So what happens as it tries to accelerate to conserve angular momentum is basically it gets more massive. And because that's what happens in special relativity when things get nearer the speed of light, they get more massive. So the fact that you can't go any faster, but you can get more massive is how the angular momentum is conserved, and basically the whole thing just gets turned into energy, which is what happens anyway in the black hole. So that the momentum turns into effectively kinetic energy, which is kind of how, even from within the event horizon, there would be radiation floating around in there. There must be a very high energy field, and in some ways that relates back to the question about the differing masses of black holes, and of course energy and mass are related directly by E equals mc squared. So that perhaps is another way of looking at the varying masses of black holes. It's how much energy is locked up in them. Okay,
so that's the answer.
You don't look.
I don't feel any wiser.
No,
it's confusing.
I think you would.
John probably understood what you were saying. That's all I'll say to it. But yeah, they are just such and the fact that we have not yet seen one makes it even more complicated, because we know they're there. Everything proves that they exist. We know a lot about them, but we haven't ever seen one. So we're still working on that.
That's right. The Event Horizon Telescope, hopefully we might get some results back from that before too long, so we can actually see a black hole.
Yeah, that will be good. And the other thing that sort of confuses me, Fred, is you keep telling us that the universe is 13.8 billion years old. I mean, we've been doing this podcast for a long time. Wouldn't it be 13.9 billion years old now?
Maybe so, yeah.
I don't know. Yeah. It's a
just how old
figure, isn't it?
How old we make our listeners feel.
Indeed. All right. Thanks for your questions, gentlemen, and we do appreciate the input, even if I don't understand some of the time. I think that's fair. And keep them coming in. Look, we're getting so many now, it's become almost impossible to cover them all. In fact, it has. We do try to answer some of them directly on Facebook that have been covered in previous episodes. But if it's something new and refreshing and confuses me, Fred always loves to do them. So keep them coming via our Facebook page or whatever platform that you have access to communications to us from. I think that made sense too. And thank you as always, Fred. It's been a pleasure.
It's been a pleasure talking to you too, Andrew, until you started putting prepositions at the end of your sentences, which of course we were taught never to do.
Yeah, I ignored that lesson. Actually, I think I was sick that day. Pretty sure I was too. Anyway, we'll catch you next time.
Yeah, to catch you next time, Andrew. Good to talk. Thanks again.
Fred Watson, astronomer, joins us every week here on Space Nuts, as you do too, and we appreciate it. And we'll talk to you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.